Hi, my name is Tom and I'm in Professor Liu's Physics 316 class at the College of Staten Island. For our final project, we were asked to analyze a dynamic system and then try to improve it a bit. With that being said, let's get into it. Today we'll be looking at a two-wheeled robot. Robots that move with wheels typically have two driving wheels that are connected by a motor and a single auxiliary wheel that helps it balance. However, that third wheel often slips. The robot shown here aims to fix this by removing the third wheel and using a pendulum to balance instead. Our goal is to find the equations of motion from this dynamic model of the two-wheeled inverted pendulum robot. Our robot has 3 degrees of freedom. It can move forward in the x direction, it can pivot about the y-axis, and the pendulum rotates back and forth about the z-axis. This means we'll be using 3 coordinates and 3 equations of motion. Our coordinates are x, which represents how far the robot is moving forward, theta, which is the angle of the pendulum, and phi, which is the angle the robot is turning. We start by finding position and velocity equations of each coordinate for each of our masses. Lowercase m is the mass at the end of the pendulum. Capital M represents the wheels and the body of the robot, basically everything else. The documentation for this robot provides equations of motion, but these use Kay's dynamics. Instead, we will be using Lagrangian mechanics to derive equations of motion. While this method is different, the results are equivalent. Before we find our Lagrangian, we need to find our kinetic and potential energy. Potential energy is easy because we only have to find it for the smaller mass. The larger mass is on the ground, so there is no need to find it. Kinetic energy is a little trickier. Not only do we need to find it for both masses, but we need to take the velocity of each coordinate into account. This gives us a sizable equation. I've gone through the trouble of expanding it so we can see the individual terms more clearly. We find the Lagrangian by taking the potential energy we found before and subtracting it from the kinetic energy. This gives us a long equation that we can pass through the Euler-Lagrange equation to derive equations of motion, which are shown below the Lagrangian. How does this work? Well, we derive each term with respect to the derivative of the coordinate we're looking for, and we take the time derivative of that. This eliminates any terms that don't contain the coordinate in question, so we wind up with the equations of motion that are much shorter than our Lagrangian. In this case, there are 1 or 2 terms each. The Lagrangian is a huge help when we're working with a system that has a lot of moving parts. Next, we're going to modify the robot. Our goal is to make it even more stable by reducing vibration. We'll do this by shortening the length of the pendulum and adding shock absorbers to the wheels. The equation of motion for a pendulum's vibration is shown here. We can see that it's directly proportional to length. Therefore, if we cut the length of the pendulum in half, we have the vibration. Now, I'm mainly doing this to show how much we reduce the vibration with such a simple change. In practice, reducing the pendulum's motion by this much actually stops it from balancing the robot, which defeats the purpose. We might be better off shortening the pendulum by a smaller amount. Shock absorbers damp the vibration caused by the wheels. Damping is the restraint of vibratory motion. We can measure how much the shock absorbers dampen the wheel's vibration by using the formulas for natural frequency and the damping ratio shown here. And that's about it. One thing you may have noticed is how lengthy some of the math was. It seems like an awful lot for a box with wheels, right? Well, believe it or not, this was largely due to the fact that the robot could turn. If we restricted the robot to moving in just one direction, we'd actually wind up with a very simple cart and pendulum problem, like something you'd see in a textbook. Every degree of freedom makes a big difference. Speaking of small changes with big impact, our alterations to the system were very simple, but reduced vibration significantly. All we really did was add a pair of springs with masses on them, and we shortened the end of a pendulum. So, I hope you guys enjoyed the video, and let me know if you have any questions. See you later.